Good morning, everyone. So, welcome to another lecture in platform technologies. So,
Good morning, sir.
the way this course is going to be, I briefly shared the structure of the course last week as well, but the sort of the topic areas that we will be covering would also cover some sort of fundamental foundational concepts as well. So we will also cover some of the sort of advanced sort of application type technologies, but we will also be covering some of the foundational theoretical topic areas. So in that, we are going to look at processes today. So when we say processes in computing, what we mean by a process is that is an instance of a program, an instance of a program that is currently running in a computer. So if we say, for example, have a piece of software written as a code and available as an executable on your hard drive, for example, at that point when it is stored in the hard drive, that is the program that we have. But when we open it and when we run the program, that's when we call it the process. So by having the concept of this process, it enables us to do a number of things. So one of the things that you would understand, say, from the computers, the type of computers that you would be using on a regular basis, that you are able to run a number of programs at the same time. So you are able to run, even at this point, if you are running on a computer, you may be having Zoom meeting opened, you may be having maybe a PDF reader opened, maybe a web browser opened. So a number of programs you may be running there. So the ability to run these multiple programs at once comes from the concept of a process. So what we would have in these multi-programming systems or computer systems that can run multiple programs at the same time, we would have this concept of process, which is a program running at a particular point in time. So then with that, we would be able to run multiple programs and switch between them as needed. So that is a very basic concept of a process. So that is the instance of a program that is currently running in our computer. So a good way to understand a process is the difference between a recipe and you actually cooking. So say you have a recipe to make a particular curry, so that recipe is the program. So it will say what are the things that needs to be done. It will say if you add this, then you do this, then you do that. So it is the set of instructions. So similarly, a program is basically a set of instructions that is written in a programming language and possibly that is converted into an executable for the particular system. But it is still a set of instructions that is available there. Whereas a process is you are actually running the program. You are actually doing the recipe and making something. So the difference is you can have the same recipe and cook the same curry at different days. So you can use the same recipe and cook something today, and you can use the same recipe and cook something tomorrow. Both instances of cooking will be different. You are making the thing repeatedly. Similarly, you can use the Word program today and write a document, and you can use the Word program tomorrow and write a different document. But still, you are using the same set of instructions to do a task. So that is the main difference between a program and a process. The program is the set of instructions that is going to say what needs to happen. A process is, on the other hand, is the one instance of that happening. So you are using that program at a particular point in time. Then you close that, you close the system, then you come back another day and run the program again. That is the new instance of the process. It is the same program but at a different point in time that is running. So that is the main difference between a process and a program. So within this type of computer, the standard type of computers that you may be thinking about, that you may be using, what we have here is the concept of a sequential process. So what we would have is, say, think about a computer that you use and what that computer can do. So underlyingly there will be an operating system that is doing certain things like file management, and you are logging into the computer, and all these things are managed by the underlying operating system like Windows or Linux or any operating system that is going to do some of the things. So that is a level of software. Then you will have a number of other software, and each of them are going to do different things. So you may use a word software to do typing and word processing. You may use a browser to go to the internet and visit websites. You may use another application for teleconferencing like Zoom meeting. So different software may be used for different purposes. So what we have here is we separate these functionalities into separate pieces of software, and that in turn would become separate pieces of processes. So then what we can do is we can run all of them at once. So if we don't separate them into different processes, what we will have to do is we will have to have a system that can only do one thing. So computers of sort of older times and all, they were able to run only one program at a point in time. So they would be able to, like, they were single purpose sort of computers. They would run a particular software application, particular task, and they will complete that. Whereas now we have computers that can do multiple things at once. So that is the type of computer that we call the multiprogramming computer. And how do they do that is by switching between these processes from time to time. So what we would have is we can have a computer where we are having a number of programs available. We have a number of programs available and we are running them all at once. So say we have a word processor, we have a browser, we have a meeting software, and we have a media player. So if we have all these 4 programs, and you may want to run all these 4 programs at once. So what we would do is what is called a rapid switching. So rapid switching is the approach that we would take when we are running these programs at once. And what do we mean by rapid switching is we run this program for a period of time, then we go to this program for a period of time, then we may go to the third program for a period of time, then we may go to the fourth program for a period of time. Then after we have gone through all of them in a cycle, we may again come back to the first program here. So at a particular point in time, we can still only run one program because we only have one processor. So we are assuming that we only have one processor. If we have one processor, we are still only be able to run one process at a particular point in time. We can only do one computation at a particular point in time. But if we have 4 processes to run, what we would do is, say we take 1 second time period, we split it into 4, give each process like 250 milliseconds. So every 200 milliseconds we will switch between processes and each of them can continuously do something. Then from the end user, from the user perspective, you would still see that all of these programs are running, but in reality they are running sort of switching between one another. So they are not continuously running. This will run for like 250, then the next one, and then the next one. But from an end user perspective, you will see that all of them are running at once. So that action of seeing them as being running in parallel but not running in parallel in reality like this, so they are like switching and at a particular point not two are running, but you will see as running from a user perspective. That is what we would call as pseudo parallel. So they are parallel but they are not really parallel. They will seem like parallel to the user. The user will see that they are like parallel, but in reality they are running one after the other. So we will call that a system that is running in pseudo parallel mode. So that is the basic process model that we would use in multiprogramming computers. So what we would have here is, say, if we have these four processes and if we observe them over time, at every point in time, say at this point in time, only one process is running, others are not actively running. Then say at this point in time, another process is running. Now B is running, A is no longer running. Here now C is running, the others are not running, and so on. If we go every point in time, only one process will be running, only one program will be active at a point in time. So we will have them independently, we will have them running independently, but we will switch between them and we will only have one of them running at a particular point in time. So is that clear? Do you understand how this multiprogramming works and how process switching works? So that is one of the fundamental ways how we are managing to run multiple programs in computers even when we only have a single CPU. So even when we can do only a single processing, because like say from a hardware perspective, if we have a computer, there should be a CPU, and if the CPU is the only one that can do processing, so within a computer the CPU is the only one that can do any computational task. If we have only one of them, that also means we can only run one process at a particular time. So for us to do multiple programs, we'll have to do this process switching to achieve this parallel pseudo parallel environment. So when we have the concept of a process, so now we have this program that is written and stored in the computer, that is there, that is the program, and then we run a program, it becomes a process. So we have the concept of process. So now the question is, how can a program become a process, or how a process can be created? Because if the program is just stored on the hard drive, then that doesn't mean it's not going to run. Something is going to make it run, make the process created and run. So there are a number of common possibilities how these processes can run. So we'll look at each of them briefly. So the first case, or the first way a process can be created, is what we call system initialization. So you come to your computer, you switch on the computer, then something happens. So the main thing happen, one of the fundamental things that would happen there is the computer will have some form of instruction stored that will point to where the operating system is. So this will be what is called a boot sector or a boot partition or something, where computer will go and check for what to run when something is switched on. Then that would point to something that is specific to that operating system. Then that program will be run, and that would be the first process to run. So when you start a computer, some programs need to run, and they will start as some processes and run. So that is the first type of process creation. So that is when you switch on a computer, then it will create some processes. So it may create one or more processes when you have switched on the computer. So then the second category of process creation is what is called a process that is created by another running process. So what we have here is, so you have started Windows. So we have switched on your computer, you have Windows operating system. So you start Windows. So when you start Windows, what do you observe when you log into the screen? Or if you have password, when you log into the screen, what are the things you observe? Is it just Windows that is there, or are there other processes that are also running? So you may have an antivirus software, and most of the time when you log into Windows, that antivirus software is also now running. You may sometimes have some other updating software, media player and things like that. They may also be running in the background when you start your computer. So how those processes got started? So Windows got started by system initialization, but then there are these other processes, they also got started. So they are the ones that are being started by other processes. So for example, if Windows is one process that is starting, then it is going to start other processes that is needed by using what is called a process creation system call. So we will have what is called a process creation system call, and the operating system can use this and go into the system and open additional programs. So it can open an antivirus software, it can open a media player and so on. Depending on how the system is set up, it will open additional processes like that. Then the third category of process creation is what we call as when a user requests a process to be created. So after you have switched on the computer and you have logged in, so now you see some of the processes are already created and available, and now you go in. So when you go into the system, now you want to use certain programs. You may want to open the browser and go to a website. So you have to do that. Or you may want to open Word and type some documents. So there are other programs that you may want to use, and you are requesting those processes to be created. So these are processes that are created by a user request. So a user who wants to run a particular process can request that to be created. And the fourth category of a process is what is called processes that are created by a batch job. So we sort of briefly touched upon batch jobs previously, I guess. But basically the idea is a batch job is we have a number of tasks that need to be completed, and they can be grouped together. So they are a similar task that needs to be repeated, and that can be repeated as a batch job. A good example to remember is if you are a telecom operator and you are generating monthly telephone bills. So for each user, you need to go through the same process to generate that bill. Because generating the bill, the instructions, the program to generate the bill will be the same for every user. You need to go to the database, check their call logs, calculate the total call, whatever usage, and generate a bill. So that is the same program needs to be repeated for every user. So in such a scenario, we can organize that into what is called a batch job. And for each user, or each customer, we will create a new process to do this. And each of these processes can be created as a batch. That is what we will call a batch job. So here that batch job is the one that is initiating or creating these processes. And one of the other things that you can sort of see across all these things is, in any case, process creation will somehow be created using what is called a process creation system call. So this process creation system call that is provided by the operating system will be the one that is most likely be used at any instance. Say for example, maybe system creation is the only sort of exception where it is initially started from sort of an operating system process. But after that, all of these are created by some process. So the second one, anyway, it is created by a process creation system call. One process is calling other processes. In the case of a user request, normally you are going and clicking on an icon or running a command on a command line. In all these cases, you are also interacting with another existing process. So because like even in Windows, the window manager or wherever you see icons is also a process. So you are interacting with that process and telling that process to open another process. So that is creating another process. So the idea is like these are sort of 4 common ways processes can be created, but one of the commonalities among all of them is what is called this process creation system call. Is that clear? Does it make sense? Are there any doubts about that? So the next thing is, once we have created the process and our program, our use of the process is going on, then at some point in time that may needs to be stopped. So we may have a number of reasons why a process may have to stop. So again, we will identify 4 common scenarios where process termination may need to occur. So the first one is, you have a program with a set of instructions, and when you are running that as a process, it has gone through all the instructions, it have completed all the tasks, and it finishes. So that is what we call a normal exit. It has executed everything normally and it exits without any problem. The second category is what we call a error exit. So here what we have is, again, you have a program with a set of instructions, and here at a particular instructions you find an error. So say you go through a program and that program at some point needs to read a file from a storage. It needs to read a file from the storage, but that file is no longer there. That file got deleted for some reason, but the program finds that as an error. So the programmer, so when you are programming as a programmer, you may write a code saying, if file exists, then open. If no file exists, that is an error. So you, as a programmer, you identify whether it is an error or not, if using an if condition, for example. Then if you identify that as an error, you would say, if we cannot open that file anymore, if we have to exit, the process should exit. So at this point, it is executing up to this point. Here it finds an error and it terminates there. So that is what we call an error exit. Then the third category is what we would call as a fatal error. So it is similar to an error exit scenario. So again, we are going through these instructions. We are trying to do something, reading a file or writing a file or whatever. But here the difference is, the programmer of that process or of the program has not written a condition to cater to that problem. So the process is running, it is coming to a problem. When it comes to that problem, the programmer needs to specify what it needs to do. So unless the instructions are given, a program cannot figure out what to do. So anything that a program does, anything a process does, should be explicitly told by the programmer. Whoever creates that need to give that instruction. So if they have not given that instruction, at this point, it doesn't know what to do. It's like clueless at that point. So it will execute up to this point, then it encounters an error. It doesn't know what to do when it encounters that error. So it will exit there with what we call a fatal error. It doesn't know what to do, so the process exits, but it is not something it anticipated. So that is the fatal error. Then there is a fourth category that we would call as killed by another process. So that is, again, you have a process that is running, that is continue to run, but at this point in time, another process is issuing a command to kill this program. So for example, you are running some programs and you shut down Windows while some other programs are open. So if you shut down Windows process is going to close all the other processes that are currently running. So these processes were not exiting sort of in a normal scenario, they were closed forcefully by another process. So these are 4 ways processes can be terminated and they can close. And of these 4 ways, what we have is the first 2 types, the normal exit and the error exit. In these 2 cases, the program itself knew that it had to exit and it knew why it is happening. So in the first case, it completed everything successfully, so it ended there. It knew that instructions was there. The second case, it didn't know what to do, or rather it didn't have some access or some problems, but it knew if I have a problem, I should close now, and it closed itself. Again, it knew what is happening there. But in the third and fourth category, the difference is here they don't know that they are exiting. That process, the third category, it encountered an error, but it didn't know what to do and it didn't know it had to exit, but that circumstances it exited. So, and the fourth category, again, it is forced by outside process. So based on that, we would identify the first 2 as voluntary. So because they are doing it that in their own wish, these processes had instructions to do that, so that is voluntary. And the second category is involuntary, because here the processes didn't know what to do in that instance. So that is the main difference between the type of exit conditions. We may have a voluntary exit or an involuntary exit depending on if the process knew something it needs to exit, it will be voluntary. If the process didn't know that it needs to exit, that will be involuntary. So now, when we have these processes, so we have a number of processes that are running. We have started the process, so we know there are 4 ways processes can start. Then once they start, at some point they can exit. Again, we know there are 4 ways processes can terminate, but in between starting and ending, there should be a middle point where processes are running. So when processes are running, they are not always going to be running. So that is the main point here, because when we looked at this pseudo parallel operation mode, what we said was processes are running sort of from time frame to time frame, they are not continuously running. So even when a process starts, it is not going to run all the time, it is going to run occasionally, or it's going to switch between other processes and run. So when it is running like that, we will identify what is the state a process is in a particular point in time. So we would identify 3 main states a process can be in. The first one is process is running. So basically that is the point where it is actually running. So in this point, that process is currently running. Then if a process is running and then after say 250 milliseconds, we say, okay, process A now stop, now process B can run. So at that point in time, process A is ready to run, it is able to continue to run, but we have given that time to another process. So it is ready, but it is not running now. So that is what we would call as ready. So they are temporarily stopped until another process is running. So we have multiple processes running in sort of pseudo parallel mode. So we will have some processes actively running at one process actively running. So that is the running state, and all the other processes waiting to run are ready state. Then we will also have a third category of state that is called a block state. So these are the things, or these are the processes that are waiting for something to happen from outside. Say for example, you are opening a program. So you open the program and that program asks for a username and password. Until you give the username and password, that program cannot do anything. That process is not going to able to continue with instructions. Say for example, we have a process with a set of instructions. So these set of instructions. At this set of instruction, it is going to ask for username and password. So until the user is typing the username and password and that information is given back to the process, that process is not able to continue. So it will stop at that point and wait. So likewise, waiting for something external to happen is what we call as a blocked state. So it can happen for, say, user input from keyboard, or it is reading a file, or it is writing a file. So it needs to wait until something is complete. So it cannot do any of those things. So that is again a third category of process state. So it can be running, it can be waiting ready, or it can be waiting blocked. So in blocked waiting, it is not being able to do anything at that point. In ready waiting, it is ready to do something, but there's no time to do that. So then when we have these four process states, we can identify four different ways. These three process states, we can identify four different ways they can switch between these states. So what we would have here is, we would have a process that is, say first it is running. So we have a process that is currently running. So when it is running, the other thing that it can do is, say the time is finished, so it is running, its time frame finished, so now it needs to stop. So now it will go to what is called the ready state. So it was running, it goes to the ready state and waits. Then when that other processes are finished and when it is going to be getting its time again, it can go back to what is called the running state again. So normally processes can go in the loop between running and ready state. Then, so they can go to running to ready and ready to running. Then the other scenario is when, say, a program is blocked. So when it is waiting for input to happen, input output to happen, for example, it will go to the blocked state. So when it is running and it can no longer run, so it will go to the block state. So then from that, say if the input becomes available, it cannot go back to running directly, because when it blocked, some other program started running now. Because like when something goes to ready, a new program starts running, or another program starts running. When it goes to block, also another program starts running. So now something else is running there. So it has to come to this ready queue and wait there for its turn. So ready is the point where everything will have to go wait until they can run. So even if it is blocked for a period of time, it has to come to ready before it can continue running. So from an operating system point of view, we have this, we have the concept of a process. We have certain ways a process can be created, terminated, and few different states. They can be running and waiting, ready and waiting blocked. So we have this concept of a process now. So we have that is there. So now from the point of view of an operating system, it needs to implement how this can be done. So how it does is what is called a scheduler. So scheduler is the operating system component, the part of the operating system that is going to manage these processes. So this scheduler is the one that is going to be responsible to manage who is running, who is going to ready, and all these things are going to be managed by the scheduler. So all the processes are going to sit above this scheduler and be managed in terms of what is the active process and what are the waiting processes. And when we think about how the process scheduler can do process scheduling and switch between these different processes, we have to think about certain things. Say you are running a process now. So say let's take Word. So you are running Word as a process now. So Word process is running for a period of time. It is continuing running. So then it is stopping here. So now you have to start another process. Say you are starting with let's say you are running the browser. So the browser process, so this is the Word process and this is the browser. Then the browser runs for some time, then the Word has to continue running. So now the thing is, when Word was running, it would have had certain information. It may have certain information stored in the memory. It may have certain things about at what instruction that it is executing now. So there could be a number of things it is doing in terms of the whole process, some background information about the process. So now when we need to come back again to Word, we need to have that information that was there previously. So if the process is running at a point in time, when you leave it and you need to come back to that process, you need to know where you were at. Say for example, if you are doing an assignment at home, so you have an assignment or you are doing some calculations in mathematics or any assignment that you are doing, you may have to do a number of steps that you need to do. So say let's take, you are writing an example report for an example. So you have to write the introduction, the background section and things like that. You have a set of things to do. So if you do certain things today and you leave it and you have to come back the next day to continue, you need to know what are the things you have completed. So unless you know what are the things you need completed, you may not be able to start from there. You may start from the beginning. So the way that you would do is you would store that information in your memories, knowing like I have already completed these things. I have to complete the rest of the things. So similarly, the process manager, the scheduler, needs to manage about what are the things that are completed in this process and restore that information here so it can continue from where it left off. So that activity of managing that will be done by what is called a process table. So a process table is a table that is going to have all these information. So all these information are necessary to manage a process over time, and when this process is leaving, all the information will be stored in the process table, and when it's ready to run again, that information will be taken out. So that is how we will be using this process table. Whenever we are moving a process to the ready state or the blocked state, we will always store that information in this table, and when they are ready to run again, when they need to go to the running state, we will read this information from the process table and restore them back into the memory or the relevant registers and so on. Then another concept that we would have that is closely related to scheduling is what is called interrupt handling. So what do we mean by that is, say we are not going to go into much more detail about this today, but briefly looking at it, say a process goes into blocked state. So a process has gone into the blocked state and it is waiting for some input output to happen. Say for example, it is waiting until a file is written on the hard drive. So you need to write a file on the hard drive. So this process is waiting until that is completed. So now, until it is completed, it has gone into the blocked state. So it is no longer running. So it cannot check anymore because it is blocked. It is not actively running. But there should be a way for the operating system scheduler to know when that block is no longer a block. So somebody has to inform the operating system. Somebody has to inform them saying whatever the reason why this process was stopped, the reason was it wanted to write a file, that writing file is now completed. So because when it says now that task is completed, now this block can be cancelled and it can be ready to run again. So the operating system needs to know when these external tasks are completed. And the way how that works is through what is called interrupts. So interrupts are basically signaling ways to signal an operating system to say a task is completed or something has happened. So it is a way of informing them saying that is completed. Say for example, if you are working on a group assignment and you are depending on few other people to do few different tasks, you would expect if one member is working on something, for them to inform you when they have completed that part so you can continue working on your part. So that way of informing this process, informing the scheduler about a completion of a task, about a completion of an instruction, is what we would call as an interrupt. So that interrupt would also be necessary for this scheduling to happen, because unless we have interrupts, this process will always be in the blocked state because nobody knows what happened with that particular request. So that interrupt would come and inform that particular, whatever the requested input or output is now readily available. Then there's another thing that we can sort of again briefly touched upon today is about why do we do this multiprogramming and what are the sort of type of considerations that we can have when we are thinking about multiprogramming using different types of processes. So the first thing is, say if we have only running one program. So let's take an example. We are only running one program. So if we take only one program, so we can start running that program. That process may get blocked for some time. Then when it is unblocked, we can continue running. We may block again. And likewise, we can stop and run for a period of time. But what we would have in this scenario is there would be a number of times or periods of time where it is not actively running. Some times are wasted in between. Then we can have certain other programs, certain other processes that may run more time. So they may only stop few times, but they may use more of the processing time usefully. So here the wasted time is only this part. So that difference between these two are what we call the processes that wait for input output time more and processes that wait for input output time less. And especially in the first case, when we have processes like this one, that is when we will have advantage of doing multiprogramming, because whatever this wasted time can be used by another program to run. Because like instead of wasting that time, we can give that time to another process to run. So when you have multiple processes, That is one of the reasons why we having multiprogramming is beneficial, because we can eliminate the wastage or the CPU utilization, wastage in terms of CPU utilization, by increasing the number of programs that we are running. But when we have all the programs that are sort of input output waiting type programs, then the utilization cannot go up anyway. So if we have certain programs that can utilize the input output more, then we can gain more sort of IO utilization. So are there any questions on things that we have covered so far about processes? So if you have any questions as we go along, please feel free to put that as a chat message, or you can also speak if you like. Okay, so continuing. From processes, so we identify processes as these programs or instances of programs that are running. Then we also have another concept that is fairly similar to processes called threads. So one of the things that we may have is, even within a process, within a single process, many multiple things, many different things may be happening. Say for example, a simpler program like word processor, Microsoft Word or any sort of word processing application. If we take that for example, the basic task is you are typing some documents, so that is the basic task you are doing. But while you are typing, there are a number of things that may happen. So it is going to take your user input and present that in a sort of formatted way. So there should be some sort of formatting happening as you are typing. Then most modern word processors also do grammar and spell checking. So that grammar and spell checking is also happening in the background. So that is also happening while you are typing. And most of the word processors also do what is called auto saving. So they will save the documents periodically. So even if the computer crashes, you may have what is called an auto recovery kind of an option, or it may auto save the document every minute or some period of time. So that is also happening in the background. So now what we have is, within the same program, the same set of instructions available in the program, we are going to have a number of categories or number of different things happening at the same time. So number of different tasks are happening at the same time. So, and some of these things can also happen in parallel. So for example, while you are checking grammar, it may also need to do the formatting, and at the same time it may also need to save the file. So all these things can happen in parallel at the same time. So because they exist, this code exists within the same process, if we are running a single process, it can only do one task. So we may not have an easier way to do multiple of these tasks at the same time. So a way to address this, a way to parallelize running these tasks in parallel, we use the concept of what is called a thread. So with threads, what they are is, they are much similar to processes and you can switch between them. But the main difference is threads share the same address space because they exist within the same process. And they are also much simpler than processes in comparison. So what we can see is, an example that we can see here is what I mentioned as the example of a word processor. So you can have the part that is doing the user inputs, the part that is saving files, and the part that is doing the formatting. And all these things can happen at the same time, and the program can be split into those entities or those units as we use. And another example that we can have is like, say for example, a web server. So you are sending some request to the web server, and in the back end it has to respond back to the request that is coming. So all the requests that are coming can be collected by what is called a dispatcher thread. The dispatcher thread is the one that is going to receive the request and manage that. And then it can have what is called a worker thread, and the worker thread is the one that is going to do this creating of the web page or collecting the information and sending back the web page. So now here what we can do is we can have a one dispatcher thread and we can have many worker threads. So similarly we can have run multiple programs, multiple processes. So what we can do is for each request we create a new worker thread, and that is going to generate the web page. So we are doing couple of things. Even within the same process, we are running multiple tasks in parallel. So we are doing saving and formatting and spell checking at the same time. So that is one way of parallelizing. So here we are again splitting the task by job. So that is, one is dispatching and one is generating the worker thread generating the job. But then we can also have multiple worker threads running in parallel. So instead of having just one worker thread, we can have multiple worker threads running in parallel. So this is again a common occurrence in sort of many sort of server-based applications and so on. This can happen a lot where you may use this type of an approach in terms of modeling your process. So how, when we compare this between, say, a normal process, so when we say a normal process, that is a process that is only having a single thread, or it doesn't have any concept of a multiple thread. So when we compare it to that, the possibility is when we have a single thread, we can only switch between the processes. But when we have multiple threads, we can actually switch between the internal threads that are available within the process itself. So instead of switching individual processes, now we can also do thread switching, so thread scheduling. So when we do like process scheduling like this, like we are going one process after the other, now we can also go one thread after the other. So that is how we would do multi-threading. So like multi-programming, multi-threading is the way we are running multiple threads in parallel. And one of the other things that we need to remember about threads particularly is threads have certain properties of their own. So they will have a program counter, some registers, some memory locations and so on that are specifically belonging to a thread. But there's a lot more things that are common for all the threads of the process. So threads on their own will have a small amount of information about them, and a lot of other information will be common for the process. So what that means is, when we are thinking about switching processes or switching threads, when we need to switch processes, we need to switch a lot of information, like a lot of information in the process table need to be switched. Whereas for threads, we will only have to switch a small amount of information. So because of these things, we will have a number of advantages when we are using threads. So one of the main advantages is we can create programs, or we can create processes that are more responsive, because we are splitting the tasks into multiple threads and each of them can run independently. What we will have is whatever the task that can be completed and finished. So That is what we mean by responsiveness. So say if there are 5 different tasks to complete, if we do it in only a single process model, we'll have to go through all of them and complete all of them before coming back and saying it is complete. But if we split that into 5 smaller tasks, we can say each of the individual small task is complete. So instead of thinking one large task is complete, now we at least have few smaller tasks that are complete. So that is the main sort of way we would get some responsiveness out of using threads. And also in terms of context switching, so context switching is switching from one process to another process or one thread to another thread. As we said, threads are lightweight. There's not a lot of information about threads. It will be easier to switch from one thread to the other. So because there's not a lot of information here, it will be easier to switch from one to the other. And because threads within the same process can run independently, because like within the same process itself, we are going to have these individual threads that can run in parallel independently. One of the other advantages we can get is in sort of computers that have multiple processors, we can run all of them also in parallel. So we can run each of them in different processor in parallel, again utilizing a lot more advantage. So that is why we would use sort of multi-threaded applications a lot in, say, for example, video processing, sort of highly data processing heavy applications. We would try to build those as multi-threaded applications because they can make use of these multiple processors or multiple cores of processors available in computers. Then another advantage is because they exist within the same process, all the resources are still common. Say for example, if you allocate a printer for a process, all the threads within the process are also allocated that because they are still part of the process, they are still within the process. So now they have that advantage there. Then another advantage that we can have is what is called communication. So what we have here is, say again, when we have multiple threads and all of them within the same process and all of them are going to share the same memory space. Because they are sharing the same memory space, now all of them can share information between them. Say for example, if we take the example of the word processor, when you are typing a document in the word processor, it is the same information that needs to be formatted, the same information needs to be spell checked, and the same information needs to be stored on the disk. So all of these things, all of the threads, all of the tasks by individual threads are working on the same information. So they can share that and they can communicate among themselves and do those more effectively. And by doing these things, by dividing them into these multiple threads, what we get is we get more tasks completed within a period of time. So we get enhanced throughput of the system. So that is mainly about threads and processes. So threads and processes are going to be the foundational elements of things that are running in a computer. So that's why we looked at them, because whenever we go into sort of advanced topics about how we are managing sort of multiple things running in a server, how we can improve the performance of these various things, we need to understand the fundamental unit of things running as processes, so we can better understand how we can manage those. So now from there, if we continue further and think about some of the challenges when we would have when we do this process type approach. So now we have gone into this concept of process, and when we have taken up this process concept, we are going to have some challenges compared to just running one task in a computer. So if we are running one task in a computer and that is going to execute instructions one after the complete, there is not a lot of issues with that. But when we think about multiple processes running, now we may have some additional requirements here. So sometimes these processes may need to communicate between themselves. So for different reasons, these processes may need to pass on information. So for example, a process may generate some information, and that may be the input to the other process. Say for example, you may need to extract some information and then give that to another process to compute, and another process may use that to do some other computations. So there may be dependencies for information passing between as well. Then also we may want to avoid two processes being in sort of what we call as a critical region at the same time. So what we mean by critical region is we don't want two processes to do something that is competing for the same resource, for example. So we don't want two processes printing at the same time, or we don't want two processes utilizing the same resource, or we don't want two processes writing a file in the same location. So these are some of the challenges we want to avoid, and we do this by what we call as inter-process communication, or rather how multiple processes can sort of share information among themselves to manage them running in sort of a multi-programming environment. So we have a number of approaches that we can take to do IPC or inter-process communication. We are not going to discuss a lot of them in more detail today, but we will sort of briefly touch upon some of these in today's lesson. So one of the reasons why we need to have inter-process communication is what we call as race conditions. So what do we mean by race conditions is, say we have two processes, say here process A and B. When we have two processes like this, and then when they need to access when they need to utilize a shared resource. So for example, they are writing a file into a spooler directory from where something will get printed. So just as an example. So now, if process A is first running, and while it is running, it is going to ask what is the place where it can save a document. What is the location it can save a document? So then the response it gets is location 7. Then at that point, we do a process switching. That one go to the ready state, and process B comes from ready state to running state. Now process B goes and asks what is the free space. Because process A hasn't written anything yet in this location, that is still freely available. So now process B also thinks 7 is the free space. So now both of these processes are thinking 7 is the free space. Now again a process switch happens. Process B goes to ready state and process A comes back to running state. And process A will now think, okay, now I can continue writing. I already know I can store that in 7. And process A will go and store that information in 7. So now 7 is occupied by whatever the information that came from process A. Now at this point, process A again goes back to ready state after another switching. Process B comes back to running, and now process B have some other information. So process B also needs to store. It also thinks, okay, it can store in 7 because that's the last information it had. So it will go and store the information in 7. So it will take the memory space in 7, and whatever the information in 7 will be now from process B. So now after all these completed, what we will have is that particular shared resource, that particular memory location is now occupied by whatever the information is from B. A thinks it has already stored, but that got replaced accidentally. So now that is an issue that we will have. So this is what we would call as a race condition. So within the set of process instructions, program instructions, we will have certain parts that we don't want to skip and give it to other one. So if we want to write something in a disk, we need to start and finish completely. Otherwise, other resources, other processes may compete for that shared resource, and undesirable things may happen. So like two processes accessing the same memory location. So to avoid this memory, so this type of memory access issue or this race condition, we would sort of want to have a number of conditions met. So the first one is what is called mutual exclusion. So we will identify this part where it should not be skipped as a critical region. So a critical region in a program is where it should finish everything or not do anything. So if it starts to write a file, it should finish writing the file before completing. So it shouldn't like halfway write the file and finish. So if, for example, if it is printing a file, if two processes want to print a file, it can't be like half page is printed by one process and the rest of the half page is printed by the other process, because you have to at least finish printing one complete page before continuing to the next one. So that is like what we would identify as a critical region. So if a process in critical region, we want to have that process complete its critical region before the next process can come. So what we want is no two processes can be in their critical region at the same time. So that is mutual exclusion. So if one process is in critical region, it has to complete that before another process can come into a critical region. Then the second one is no assumption. So even when we have these critical region type of an approach, we cannot do that based on assumptions about the speeds of the processor, for example. We cannot say we will wait for 5 clock cycle of a processor and then continue. We cannot do that because we cannot anticipate how processing may happen. Processing may be slower, faster, depending on how all these things happen. So as a programmer, you should not be designing things in that manner, thinking about what is the fast speed of the process and so on. You have to think about completion of tasks and things like that. So that is no assumption. Then what we call progress. So if a thing is running, a process is running in the critical region, say for example, if it is writing a file, another process from outside should not be able to block that. If it is writing something, it should complete that. Others should wait until that critical region task is completed. But on the other hand, what we have as starvation, that is a process should not always say I am in critical region, I am doing something important, so nobody is blocking me. So that is because we are talking about shared resources, so other process is waiting for this shared resource, and this one can't say I am always doing something important, so I cannot share this resource. So we can think about this as from a shared resource perspective as well. Say, for example, if we can understand all these four from a sort of a simple example of sharing, say, a computer resource, for example, in a laboratory. So if you are working on that computer at a particular point in time, so working on assignments or something, then there should be a mutual exclusion that you finish and the next person starts working. Then you cannot have assumptions in terms of how fast you may complete or how slow other person completes. Again, if you take a particular amount of time to complete a task, then you should be allowed to complete that task in that period of time. Then progress is if while you are working on a critical assignment, other person cannot come and say you have to stop and they want to work on that. You have to given the chance to complete that assignment. But at the same time, you can't be saying I am working on this important assignment and use that laboratory computer all the time, because other people are waiting to use that resource. So you cannot starve the other people from using that. So that is the conditions that we would have to avoid this race condition regarding shared resources. So there are a number of ways that we would number of mechanisms that we would use to avoid these race conditions. And the first one, or the first approach that we would take, is what is called mutual exclusion using critical region. So what we do here is, if a process enters the critical region, so at this point, if a process enters the critical region, and later on, if another process wants to start here or enter the critical region there, we will not allow that. We will not allow B to start its critical region until A has completed. So once A has completed, then we will allow B to start its critical region. So at a particular point in time, only one process can have its critical region. So here we had B blocked. So that is critical region, mutual exclusion using critical regions. So if A is writing a file, we will wait until A finishes writing the file before B can write a file. So that is a basic way we would implement this. Then again, we can have a number of other approaches, like, say, for example, we said we will have interrupts coming from outside, stopping running processes to instruct them doing something else. But by an external interrupt coming while we are in this important task, when we are running a critical region, we may stop that. So what we would do is, we may stop any external interruptions until we finish this critical region task. Similarly, we can use what is called lock variables. So what we can do is, we can lock certain resources, saying process A is now using the printer, so no other resource can print. Then once A finishes and releases the resource, then process B can continue using that. So that is again another approach we can use to manage this mutual exclusion part. Then again, we have a number of other approaches that we are not going into detail, like strict alternation, and then there are other sort of algorithms or processes. We will not be going to them in more detail in this course because they are not critical for this particular course, but you need to know that there are other approaches as well. So now we will look at some what we call some classical inter-process communication problems. So we'll sort of again briefly look at some of these as well. Say, for example, one of the common classical inter-process communication problem is what is called a producer-consumer problem. So a good example that this may be happening is in the context of a lecture. So as a teacher, I may be producing information at a particular speed, and I am delivering those information. Then as a student, you may be receiving those information as a consumer. You may be consuming that information at a particular speed. So if I'm speaking at a particular speed, and if you are understanding at a particular speed, there may be a difference in these two speeds. So I may be producing at a particular speed, you may be receiving at a particular speed, and there may be a mismatch between these two. So then what we may do in terms of that is we may use what is called a mid buffer. So we may have a buffer here, and using the buffer we may be able to store information intermediately. So say in the case of, say, we are our process is creating some information that is creating at 1 Mbps. So that is the speed our process is producing information, whereas our communication or the network communication is producing information at only 200 bits per second. So it is doing 200 bits per second. So then we may have a buffer here to store this information, but even that buffer may sometimes go full. So as long as producer is putting information here and consumer can take that out before the buffer becomes full, that is okay. But if the buffer becomes full, some information will be lost. So that is one of the things that you would observe in sort of these online lectures is sometimes you may lose some information due to buffering and things like that. That is because of I am producing information at a particular speed and trying to send through my network, but my network is not fast enough to send all that information at once. So it is eventually losing some of the information. So that's why some of the frames are being dropped. Sometimes the audio is dropping. It is because of this problem, the producer-consumer problem. The information is generated at a particular speed. It is consumed or stored or whatever at another speed. And in between, we will try to manage it through a buffer, and still we may not be able to use it at the receiving end. So if the producer continues to produce at a higher pace, at some point we will lose. If the producer stops at a point, then consumer may be able to access everything that is in the buffer. Then another problem that we may come across is what is called a dining philosopher's problem or shared resource problem. So what we have is, here we have a limited number of resources that needs to be shared among all the different processes. So for example, if we only have one printer and 5 different processes need to print, which process prints using that file? Or say in this example, it is like 5 chopsticks and we need 5 people eating. So how they can share that resource and eat. So again, any sort of shared resource problem we can understand through this. That is how we are going to share between different users, different processes, and so on. Then another problem is certain applications, for example, especially sort of database type applications, we can have certain users writing information, certain users reading information, and what we can have is, we can have many people reading information, that is not a problem, but we may want to have only one people writing or one person writing, because multiple people writing at the same time may corrupt the data. So the same problem of multiple people accessing the same data store and corrupting or replacing the data, so that problem could be there. But we can have multiple people reading, because when they are reading, they are not affecting the data, they are just taking it out. So reading can happen for multiple people, but writing can only happen for a single person. But at the same time, people writing may need more higher priority, because that's an important task to be completed compared to reading task. So again, this is again certain things when we think about managing multiple processes. So these are again sort of inter-process communication sort of problems that we may come across when we think about larger environments, larger processing environments, computing environments where we are running multiple programs. These are some of the problems that we may come across in the context of processes and threads. So that brings us to the end of discussion about processes today. So we have covered the basics of processes, so understanding what are processes sort of conceptually and how they function in a sort of a foundational computational environment, and sort of various ways they can be created, terminated, and so on. And we also briefly touched upon threading and how multi-threaded computing can be used, and sort of what are sort of the advantages of utilizing them and how they can be used. So that is a sort of fundamental look at processes and threads and how they are utilized in sort of computing environments. So are there any questions on the things that we discussed so far today? On the various topics that we discussed today, are there any questions that you have, any doubts, any clarifications? So, and as always, you can ask these questions while we are in the live class. Always, I will post. I will have a LMS post available where you can again check, ask any questions and check any details with me if you have any doubts and things like that. And also you can email me or text me or something if you want any sort of clarifications as well. So if there are no other questions, we will conclude the lesson for the day. The lecture slides and the recorded lecture video will be available on LMS. And as always, you can contact me with any clarifications and doubts. Until next time, thank you for joining on this lesson. See you. Bye.